we always talk about space as this, like, huge thing, right, with stars and galaxies.
Right.
But what about the space that's, like, right here around us? You know? Like the
Yeah.
space that our desks and our coffee mugs
Exactly.
exist in.
Yeah.
And, like, did you ever think that even those simple shapes, a cube or a pyramid,
Yeah.
could be hiding something, like, really deep down?
Totally.
Today, we're doing a deep dive into a document all about a new way of understanding the geometry of space.
Okay.
And it's called CPS Geometry.
All right. So
I don't know.
it sounds a little intimidating.
It does sound a little intimidating,
Yeah.
but it's actually pretty cool once you kind of get
Yeah.
into it.
It challenges the way we think about it.
Yeah, and that's like those high school geometry classes and points and lines and planes.
Exactly.
It was all very neat and organized,
Right.
but kind of
Sterile.
very sterile.
Like an empty room.
It's a common experience. And this source points out that traditional geometry starts with the abstract instead of the concrete world. Okay. Like, think about 3D shapes, cubes, pyramids,
Right.
platonic solids. There are only a few, and they're all over in nature.
Okay.
This document uses those shapes as like a starting point for CPS geometry.
Okay. CPS geometry. What is that?
So CPS stands for close packing of spheres.
Okay.
Imagine you've got a bunch of spheres, like oranges,
Okay.
and you want to pack them together.
Like in a grocery store.
Exactly like oranges at a grocery store.
Right.
That natural arrangement is a foundational concept in CPS geometry.
Interesting. So instead of abstract points and lines, we're starting with like a fruit vendor arranging oranges.
Yes, exactly.
That's kind of cool. That's a lot more tangible
Yeah.
than like some dot on a page.
Exactly. It's a much more intuitive way to understand shapes.
So how do we get from the oranges
Yeah.
to those like symmetrical shapes that we were talking about?
Good question.
Yeah.
If you connect the center of all of those oranges, you will actually start to see the outline of some of those platonic solids.
Yes. So if you imagine a sphere at each corner of a cube, and then you put more spheres in between them, you get a close packing that forms a cube.
Oh, wow.
Yeah,
So you're telling me that those shapes are, like, hidden
they are.
in a stack of oranges.
The document has illustrations.
Wow, that's kind of cool.
This is just the tip of the iceberg, though.
Okay.
What's really fascinating is how this idea of sphere packing connects to this idea that mathematicians have been thinking about for centuries.
Okay.
The division of a line into extreme and mean ratio.
Now you were just using big words to make me feel like I didn't pay attention in high school.
I know.
But what's so special about dividing a line?
It's not just any division.
Okay.
It's a very specific ratio called the golden ratio.
Yeah.
It's about 1.618, and you find it everywhere.
Really?
Sunflowers, the human body.
Wow.
And it turns out that this golden ratio is super important to the concept of similarity.
Okay.
And that's at the heart of this new way of looking at geometry.
Okay. The golden ratio. Got it.
Yeah.
How does that get us back to geometry?
Okay.
We were talking about, like, ratios and lines.
Right.
Not stacking oranges anymore.
This is where it gets really interesting.
Okay.
So the golden ratio isn't just some, like, mathematical thing.
Yeah.
It's, like, really related to similarity in shapes.
Okay, similarity. So, like,
Yeah.
shapes being the same, but different sizes.
It's more than that.
Okay.
Think about the oranges.
Okay.
They pack together in a pattern.
Right.
Similarity in CPS geometry is about knowing that that pattern exists at different sizes.
Okay, so it's like,
Yeah.
if I zoom in on a fern,
Yes.
it's still the same pattern, but smaller.
Exactly.
Yeah.
And what's so cool is that this concept of similarity, this golden ratio thing, it's actually way more fundamental to geometry than Pythagoras.
Wait, more
Like-
fundamental than Pythagoras. That's like
I know, right?
a squared plus b squared equals c squared.
Yes.
That's
Yeah.
like the main thing I remember from geometry.
I know, it's crazy, but it relies on the concept of parallel lines
Okay.
and that they go on forever.
Okay.
And that gets kind of messy when you start to think about infinity.
So you're saying that geometry that we learned in high school is, like,
Yeah.
wrong? Or, like...
Not wrong, but
Right, yeah.
limited.
Okay.
It's limited.
Got it.
And this is where CPS geometry is better.
Okay.
Because it starts with the concrete patterns instead of abstract lines that go on forever.
So instead of those lines forever, we're going with, like,
Yes.
patterns we can actually see.
Exactly.
Like in the real world. Cool. Okay.
And that gives us a new way to understand similarity.
Which is apparently super important.
Which is super important.
Got it.
Yeah, this actually goes beyond basic shapes.
Okay.
This new understanding of similarity could change everything.
Like what?
Think about architecture.
Okay.
What if we could design buildings based on close packing?
Right.
Stable and efficient.
So we're not talking about shapes on paper anymore. We're talking about
Exactly.
the whole world.
It's a new way of seeing patterns,
Okay.
structures in the world.
Okay, so CPS geometry.
Yeah.
It's like way different than what I learned in school.
It is definitely
Is
different.
it like a totally different thing, or is there like some overlap?
Let's see.
So this isn't about like using different rules of geometry.
Right.
It's like a whole different way of looking at stuff.
Yeah, it really encourages us to look for those underlying patterns.
Okay.
Those connections that we might not see right away.
Okay.
And those patterns might be like way more important than we think.
So we've mainly talked about spheres,
Right.
like oranges.
Yeah.
But this document also talks about some pretty complex shapes.
It does, yeah. And this is where things get really interesting.
Okay.
This whole close packing thing.
Right.
It's not just spheres, it's also more complex polyhedra.
What's a polyhedra?
So like a truncated octahedron?
A truncated octahedron.
Yeah, imagine a cube, but smooth.
Oh.
And the corners are kind of cut off
Okay.
and replaced by squares.
Like those dome things you see.
Yes. Exactly like a geodesic dome.
Okay, cool.
And so these truncated octahedrons
Right.
and these other complex shapes, truncated tetrahedrons,
Wow.
cuboctahedrons.
Those are big words.
I know, they're a mouthful.
Yeah.
All of these shapes can be made with closely packed spheres.
Wait, so you're telling me that those crazy shapes
Yeah.
are still based on that same pattern of oranges?
Yes, exactly. And that's like the coolest thing about CPS geometry.
Yeah.
It shows how these hidden connections and structures
Okay.
link all these forms together.
That's kind of amazing.
It really is. It's like this hidden code to the universe of shapes.
Okay, so like what other codes could we like figure out?
Right. Like what if we use CPS geometry in other fields?
Oh, wow.
The document mentions using it to understand crystals in chemistry
Okay.
or even cells in biology.
Wow, so this isn't just like a math theory. It could actually be used for real stuff.
Yes, exactly.
That's amazing.
It really makes you think about the world differently.
Yeah, I'm going to look at oranges differently now.
Me too.
And be like, whoa, look at all those shapes.
They contain hidden geometric secrets.
Exactly. Well, thanks for joining us for this deep dive.
Yeah, thanks for having me.
And we'll see you next time.